We present event-based stereo-visual odometry with native temporal resolution via continuous time Gaussian process regression. In mainstream event-based motion tracking pipelines, like event-based visual odometry and SLAM, grouping events to one common time is often used for trajectory estimation. This approach works to some extent but omits the temporal information encoded in each event. Meanwhile, without grouping, given a set of event features, estimating individual event states at their occurring time is also challenging. To fully utilize the temporal information while achieving per-event state estimation, in this paper, we presented an event-based stereo-visual odometry pipeline using native temporal resolution of the event data. It works with any feature detector and tracker that maintains the individual event time of each feature, featuring a tailored outlier rejection scheme for the asynchronous event feature tracklet, which provides consistent inlier selection, and also outputting a continuous time trajectory estimation, which allows the state to be retrieved at any given time in the estimation window. Here we show the full pipeline of our algorithm. Its front end creates the data representations of the event streams, detects and tracks features and performs outlier rejection of the feature tracklets, while the back end optimizes the selected inlier set to give continuous time trajectory estimation. In the following, we will talk about each module in detail. Our estimation pipeline works with any event feature detector that can associate individual features with unique event times. We demonstrate our pipeline with a basic feature detection approach based on classic computer vision techniques supplemented with times from the events. We do this by clustering the incoming event stream in a spatio-temporal window and producing two representations. Binary event frame, which simply indicates the position of events occurring in the image space, and surface of active events, which records the timestamp of each event. The first representation is used for geometric feature detection and tracking, while the second is used to look up event time of each feature. To increase the number of event tracklets and maintain a prolonged feature tracking period, we allow features to be matched in the previous n event clusters. This does serve our purpose, but in the meantime, introduces a portion of noisy tracklets. To effectively reject those outliers and maintain the good quality of inlier feature tracklet set, we use motion-compensated ransack as our outlier rejection scheme. It's based on a constant velocity motion assumption and fits a motion model using SE3 velocity. This scheme is naturally compatible with asynchronous event tracklets with unique measurement times. Here we show the event feature tracklet before and after the outlier rejection scheme. With motion-compensated ransack, the resultant inlier tracklets are more consistent with each other. In addition to the inlier set, this stage also provides per-measurement velocity, which serves to initialize the estimation for optimization in the next stage. In the back end of the pipeline, we optimize the measurement state at each event time on its SE3 poses, velocity, and corresponding landmark. This trajectory optimization is constrained by both pose landmark observations and a white noise on acceleration motion prior, which gives a continuous time trajectory that allows pose query at any time in the estimation window. To be more specific, we provide a simple demonstration to show this stage. Given consecutive event clusters, we obtain inlier event feature tracklets on them, where each feature encodes its feature position and timestamp. These individual event features define estimation states for the trajectory optimization, which is constrained by both the landmark observations and motion prior. The output of the optimization is a continuous time trajectory estimate. We tested our algorithm on multi-vehicle stereo event camera dataset, and the following are the trajectory estimation results. In summary, we present a complete event-based stereo-visual odometry pipeline that maintains the temporal resolution of event cameras throughout the estimation. It outputs a smooth continuous time trajectory estimate, which allows pose query at any given time in the estimation window. We also perform quantitative and qualitative evaluation on the real-world dataset, and shows our pipeline has competitive performance on both global and relative error. For the full technical details, please check out our paper.